Alrighty, hello everyone. Let's see. Let me bring up the stream over here. So I can see what's happening. Alrighty, so if you read the description of my tweet, you know what we're doing today. So this one is actually, I'm going to do something that I need as part of my research project. And what that is I need to very quickly be able to check whether or not a specific model satisfies a set of constraints that I have. And so let me turn down the volume a little bit. How's the volume? Seems to be a little excessive on my end, maybe. So what we're basically going to be doing is, as the buzzwords go, we're going to write a JIT compiler and we're going to use some things that we know about the type of model that we have to make this easier. And we're going to try to see how far we get. All right. And of course, because it's the cool thing, we're going to write it in Rust. Also because I've been writing a lot of Rust lately. What was it called? Okay. So we're going to very uncreatively name it Z3JIT. Actually, I'm just going to make a project directory. And actually, let's do the thing that you're supposed to do, which is cargo add -- lib Z3JIT. Is that not cargo new? There we go. And I've been using VS Code a lot, so that's what we're going to be doing. Yes, I trust the authors because I'm writing it. All right, and there we go. So let me fix one thing real quick. Thought I tested this earlier, but can't hurt to test again. Okay. Okay, seems audible. Sorry, I just had to check that the audio is working. Alrighty, so unfortunately we're gonna have no face cam today because my camera just refuses to show up as a device in any of my operating systems. So we're gonna have to deal with that. So the first thing we're gonna need is, of course, we need to look at how the constraints look that we're trying to solve. And the easiest way to do that, or at least the way I know how to do because I've used it before, is, hold on. We're going to use z3.rs, the Rust bindings, or a set of Rust bindings. Of course, you wouldn't find that because you think it's a URL because browsers. Well, did not want Russia either, or whatever RS is. Okay, yes. So these are the bindings that we're going to be using. However, one thing that you will very quickly notice when you try to use these Rust bindings is, unfortunately, they are a little bit lacking when it comes to exposing APIs that let you iterate over ASTs. So, for example, if we look at a function declaration in Z3, you can get the arity of it, which is the number of parameters, basically. You can apply it to a set of arguments. You can get the type, the kind of the declaration. So is it an uninterpreted function? Is it a function with a known meaning? You can get its name, and that's it. You can't get what are the types of the parameters. You can't get what is the Z3 calls it the range, the return value of the parameter. None of those things are available, unfortunately. And so what I've went ahead and done for my own project is I forked it and added those things. And I'll try to get that upstreamed. But for now, what we're going to be using is this. We can actually fetch some stuff, fetch that in to pull it up to date. And then let me go into my repo on the other end and fuck it. Get status. What did I modify in Z3 itself? I didn't think I did. Oh, it's formatting from source API. That's what, when I was reading the source code, I guess when you save it, Visual Studio formatted it, but that's fine. We don't need that. Okay. And we're going to use this branch to get what we need. Okay, so let's go here. Project C3 JIT. So the first thing we're going to need is we're going to need to import it. So I think that way that works is the 3 equals path. So first we need to clone it actually. Get clone. So by the way, we'll take a look in a second at what that actually does, like what kind of things I've added. C3.rs. But so one thing I need to do is I need to, if I want to write a JIT, I need to understand what each AST does, right? What each node in the AST does, how they work, all that kind of thing. Sorry, I just opened myself a drink. So what we need to do for that is if you look at the function declaration now, and we'll go over more what these specific fields are, like what the domain of and what is considered the range as we go here. Wait. Oh, I need to check out the right branch. Whoops. Z3, good. Check out feed information extraction. There we go. Okay. So now if we look at the function declaration again, we will see that as we go down here, there's a couple things I've added. First, in Z3 itself, function declarations are also considered ASTs. And so you can get it back as an AST. You can get the so the way that Z3 works is they have what they call the range and then the domain of a function declaration. The domain, as far as I understand it, is basically the set of input parameters, and the range is the set of output parameter, is the type of the output. So the domain is a list of types of input, and then a range is the type of the output. And you can also look here, they also have the parameters themselves. I think the parameters is what you're supposed to be using. I'm not quite sure what the difference between domain and parameters is, I'll be quite honest, but it's not going to matter for us today. I don't think. Okay, so yeah, that's basically what I've added is these things to query what's the types of our expression. And then in the AST itself, if we look at it, what you can actually see there is, let me find the actual implementation of it. I think the get sort was there already. The way you iterate over an AST is you get its children. And if you think of it in terms of the actual AST, then basically like each child is a node. If you don't have any children anymore, you're a leaf node, so you're either like a constant, a variable, I don't know if there's anything else. And oh, I did add these things because Z3 internally does what is called hash consing, which basically means it will never build the same expression twice. So let's say you make x plus 1, and then later in a completely different part of the program, you decide you need x plus 1 again. What it's going to do is internally it's going to recognize that that's the same thing and assign it the same ID. So you can by checking IDs, you can check if two expressions are exactly the same. And then they have what they call a hash, which unfortunately my Rust analyzer doesn't seem to pick up, but is in... Oh, I need to update. That's why it doesn't show up. So in the meantime, basically the hash, as I understand it, is an ID for the structure of the tree. So let's say you have x plus 1, and then in another part of the tree, in another part of the program, you build y plus 1. Well, they're not the exact same constraint. They have the same structure. Whereas if the other constraint was x minus 1 equals 0, those have different structures. So that's, from my understanding, what the ID and the hash of a constraint add. And this is nice for us because what it means is that we can tell whether or not we need to JIT an AST again based on whether or not we have it already, simply by comparing what their ID is. Then, yeah, the well-sortedness of an AST is what Z3 calls whether or not the types check out. Like, is it a function? Is any function called with the correct arguments? Are the types correct? Is it the correct number of arguments? All that kind of thing. And then for certain types of ASTs, you can get the declaration of the function underneath. So one thing that I have that I'm going to copy over from my other project again is I made a really nice pretty printer so we can analyze them as we go. And then once we have that, okay, now it should show up actually, so we can double check the documentation on that as well. I think it's here. Z3 get AST hash. The hash code is structural. You can use them interchangeably with this function. Interesting. Is unique up to structure quality. Same children, same person. Interesting. Okay, so I was slightly off on that. But given that it considers the same function symbols and all of our variables are considered function symbols with undefined meaning, I think that just means it compares for equality. We can check that in a second. I'm pretty sure it does mean that does that though. So I believe we can do something like this. Does that failed? Okay, cargo check. Why does that fail? Let me go back to my other implementation again. Oh, I also have to add this, I guess. I also have to add Z3 separately. And so that should work. Okay, nice. That does seem to work. So now that that's done, let's take a look at what we're trying to do here. What is happening? Why is it so slow? Oh, come on. I guess the first time takes a while to build. Let me grab what else I need from this. We want log, we want env logger. We probably want pet graph at some point. And sure, and if we need a command line, we can grab clap while we're at it. So now so basically what we're going to start with, I think, is what we're basically going to want is some struct JIT AST. And I think here's kind of what I'm envisioning that to look like. We want a function run that takes a model that, or I guess we can call it evaluate probably, that just takes a model and returns us a bool probably, just because we're only considering constraints for now. We don't really care about returning other types. So we're going to call that Z3. Actually, let's make our own model because I have a very specific type of constraints in mind that I need solved. So we're going to call a struct model, and all that's going to have is basically a bytes array. Because, so what we're doing here, just to give some context, is if you've ever played around with concolic execution or symbolic execution, one thing that I would definitely recommend looking at, because it's a really cool project, is Eurocom S3 SymCC, I think, is SymCC. It's a really cool tool where basically, and the funny thing is, when this paper originally came out, I thought it was kind of dumb. I'll be quite honest. I thought it was kind of stupid because all in quotation marks here, that they're doing is basically, the gist of the paper was concolic execution is slow because we're doing all these hacks to either emulate the program that we're running, or Qsym. Let me see if I can remember this one, which is also a cool tool to look at. Also, they thought it was stupid at the beginning. Was it this? No. Qsym. Oh, I think I just had them mixed up. Damn it. So this is also, after the fact, I think it's actually quite cool. The entire thesis was emulating the program is too slow, as in like going through every instruction and trying to interpret it. And speed is one of the main things holding us back. And so we're just going to make it as fast as possible and take a bunch of shortcuts. A bunch of shortcuts when it comes to solving constraints, a bunch of shortcuts when it comes to, or shortcuts in the way of we're going to do taint tracking and only execute the instructions that actually operate on symbolic data. And so they actually got a decent speed up. They got quite a decent speed up. And then it was also just well written in a sense where you could actually use it on real software. And so SymCC, what they did is it said, oh, and Qsym used dynamic binary instrumentation, I think with pin to run it. So basically they would, for each instruction, they had to hard code exactly what it did. But they did that for a decent chunk of instruction. What SymCC said is, hey, why don't we go a step further? Let's just compile the symbolic execution in. And one, that's a lot easier to write because you can do it for any architecture and the compiler does it for you. Obviously, you need source code, but what this does give you is it's way faster than even Qsym. Even with having, and they basically every time, I think they have, if you look at the, we can look at an output here at some point if they don't have one in here. Yeah, I don't see it in here. I thought they had an output where it showed how the actual code looked afterwards. Yeah, I'm not sure. But basically what this allowed them to do is just have a simple compiler pass that instruments the program with symbolic expressions and basically computes the same thing, one in real like they compute the real values, and then they also compute the symbolic values if the data being operated on is symbolic. And so this is actually quite fast now. And what that means is this is how I'm generating the constraints I want to solve. And they use Qsym's runtime in the backend. And so if you look into that, at some point you will see that where is it? Might be in the solver.h actually. But the point is, here, get input. So their entire solver only solves for standard in. And that's what we're trying to do as well. So what that means is all we need to do, and they solve for each byte. Each byte is its own variable. Input. Here, if they read some from the input, where's the part where they build them? Oh, here's where they iterate over them. Yeah. So basically, each variable is one byte of the input, and that's the same type of constraints that we're going to be solving here. So all we need for a solution is just a vector of bytes. And the nice thing about this lets us operate it very efficiently because, I mean, byte arrays are very easily handled in Rust, and they're quite fast. And also it makes it really easy for us to JIT because we don't have to deal with differently typed variables. We don't have to deal with anything to do with expressions being concatenated or things like that. We only have one type of variable to deal with. And so hopefully that makes it easier to do the JIT. So sure, let's do that for now so it stops bitching at me. So we're going to need a function evaluate that basically takes the model that we've defined, runs it through runs our JITted code with those inputs, and then returns us, hey, did that give true or false? So the other thing we need to do is we need to create it. So we need a function, and this needs a reference to self because it's supposed to be operating on the data. So here what we want is we want to take a Z3 bool constraint. Actually, I need to define the lifetime so that it knows what that is. It needs to take a single constraint and then produce us something of our type JIT. And we're going to change this to just be the implementation of our struct, but for now, we're just going to have it as a trait. So we can have the definition there as like, this is our interface that we want. Oh my God. Fine, we'll put them in the other thing and just provide dummy implementations. Impl JIT with a lifetime context. So this lifetime, by the way, comes from the Z3 bindings. Basically what that means is we're getting objects that live only as long as the context can live. And so the way that Z3 works is, and we can show that here. Let me just provide some dummy implementations so you can stop bothering me. And then this just returns true. Sure. Hey, we're done. Not quite. Okay, so basically, and the nice thing is we can just write this in here and it doesn't bother us. But if we run cargo test, it will run this code up here. Now we just wait for it to compile again. Come on. Oh. I'm going to put this at the bottom, actually. So that's out of the way. And then up here, we of course need to import our bool, AST, and dynamic is probably, actually we'll probably need dynamic to cast between the types. Okay. So now if we run cargo test, it runs our code. It says it works. Did it actually print it out? No. Can we see the output here? Hi. Just not showing me the output. Damn it. Cargo test. I want to see the output. Should help. Oops, my bad. Let's try -v. Am I just missing it? I'm not. That seems weird. Cargo test. I like how it's the first search result. Show output. Oh, I must have missed it in the flags, I guess. Test dash dash show output. What? Okay, dash dash no capture maybe? No capture. Doesn't like it either. Why do you not like it? Oh. That really is? Okay, now we get our output. Okay, so let's do a quick demonstration of how the Z3 interface is supposed to work. So basically, let's say we wanted to create a solver. And we can just kind of, go along the chain of dependencies here. We're going to create a new solver, which means we need a context, okay? So let's create a context. Context, new. And for that, we need a config. And so let's create a config. Z3 config. New, and for that we don't need anything. So that's kind of how this works, and let's go really quickly into what each of these mean. So config for Z3 is basically a set of options for how the solver should behave. So if we look here, if we go into this function, we can set a certain set of variables. So one, for example, we can tell Z3, hey, we're going to need you to create proofs for us for why things, I think for why things are satisfiable. I have never used this option before. This is some debug option. This is a tracing option. This is also some debug option. This means, this is going to be an interesting one for us because this means, hey, when I give you a constraint, I need you to not just give me a tell me whether or not it can be satisfied. I need you to also create me a model that satisfies that constraint. So we're definitely going to need that one. So type checking means normally Z3 just trusts you that you do the types correctly unless you ask it specifically. This, you can force it to type check every time. So usually what I would do is like set this when I'm testing, and then at runtime, get rid of it. This I'm not sure. I think this is like, sometimes they're not sure if the models are actually satisfied, so then they can double check, but they don't do that by default. This is also going to be interesting. If your constraint is unsatisfiable, Z3 can tell you which of the constraints you give it are in contradiction with each other. So, for example, if I do x equals 1 and then x greater than 2 and then y equals 1, y equals 1 is not the reason why my set of constraints cannot be satisfied. It's the first two constraints together that make it unsatisfiable. And so this can give you a list of constraints back that why this is not possible, basically. And this is also going to be important. You can set a timeout. So Z3, the problem we're trying to solve is NP complete, as far as I can tell. It might actually be undecidable. I'm not sure. I think it's NP complete only. I'm not sure that it's shown to be uncomputable. But so the workaround is Z3 can say it tells you either, hey, your constraints are satisfiable. Here's a solution or a model. What Z3 calls it, a model that solves them. Or they cannot be solved. They're unsatisfiable. Optionally, here's why. Here's the constraints that together make it unsatisfiable. Or it's just going to run and then eventually time out and say, I don't know, basically. It can say, I don't know for other reasons. But the main one is when it times out, you just get a result unknown back. And so we can actually see that here too. The results that the solver can give you back when you ask it for a query are unsatisfiable, unknown, or satisfiable, right? And so the timeout is basically, you can say how long you're willing to wait for it to tell you a solution. Okay, so the important parameters for us are the timeout, unsat core potentially, not for this specific project, but in general, that's an interesting one. And the model generation we definitely want. So let's set that up. So in our config, we're going to say set model generation true. And we're going to say timeout in milliseconds. What makes sense? So that would be 10 seconds. 10 minutes? 5 minutes? Let's do a minute for now. Yeah, let's start with a minute. We can configure that after too. What are you complaining about? Oh, it has to be mutable. Yeah. So, and then we use that configuration to build a context, which in Z3 slang is basically an object. A context is something that all the other objects depend on. From my understanding, it has things like a cache for all of the constraints. So every constraint belongs to one specific context and is solved and can only be composed with constraints from the same context. There's specific options to translate constraints between contexts, but a context basically holds all of the global state of your of Z3, of one instance of Z3, if you will, is my understanding. And so when we have a solver, because we need to collect a set of constraints, we need to have a context. And so what that means is we need to this context has a certain lifetime, and this is a Rust concept. If you don't know what the borrow checker is, it would probably be good to go read about it. Otherwise, some of the things won't make sense. The short answer is every object in Rust is owned by one function specifically, and you can lend it out to other functions. That's what we do with the ampersand parameter here. We're passing a reference. And that reference, by the way, can be passed either immutable, which is the default, or you can pass a mutable reference, which means this function could modify the object, but you can only ever have one mutable reference. So just quick disclaimer, the lifetime of the context means that if you say I have a variable and I want it to be you can say I want this variable to live at least as long as another variable. And so what we're saying is all of our constraints, the context needs to live at least as long as any of our constraints live, because once the context goes out of scope, all of our constraints are invalid because every constraint belongs to a context. And so this is basically a way to make Rust keep track of that for us. Okay. So that was that. And then we have a solver. And if you've done any Z3 before, you know how this works. You make a solver, you add some constraints, you check for satisfiability, and then if it's satisfiable, you get a model. Otherwise, you get the unsat core. That's kind of how that works. We can even, if we want, let me import BV real quick. So we have that. We can make a quick constraint to show that off. So again, constraints belong to a context, so they have a reference to the context. Then it has a value. So let's just say we'll just make a constant number 1 of size 8. And we'll have a variable named x. New const. And so this is going to be slightly confused. This is also slightly confusing. In Z3, what I would call a variable in like the solver, the program analysis solver slang, is called constants in Z3 because they're uninterpreted constants, which means Z3 doesn't know, there is no value given to them, so Z3 can assign one to them. And so when Z3 solves for anything, it gives you a bunch of constants and their corresponding values. So we'll name our variable x. We'll also make it 8 bits long. And then we'll say solver.assert, which adds a constraint. And we're going to pass x equals 1. Did I forget to implement AST? No. I thought I did already. Oh, I had. Okay, so now that that's done, we can then print whether or not it was satisfiable. Let's debug print it, and we'll say solver.check. And that basically tells us, gives us back the result from the solver. That result, solver check. Result. And then if result is set result sat, oh man, and then I'm probably going to need to import that. Yep. Then we can even print the model. Solver.get model. And quick detour, the model returns an option for a model, because if your constraints were not satisfiable, then you're not going to get a model back. So then you would get none back. Else if, actually we could just do the fancy thing where we say match result. And if we get sat, we want to run that. If we get unsat, let's print the unsat core, because why not? Actually, we can't. We're going to have to do a certain track, the way the unsat core works. I don't really want to do that. That's too complicated for now. It's not hard. Basically, if you want an unsat core, the way you do it is you label every constraint with a specific identifier, and then the unsat core gives you a set of identifiers back, and then you have to map them back to constraints. But I don't really want to keep track of that right now, so we're not going to do that. Oh, and then I forgot an opening brace. Otherwise, we do nothing. All right. So now if we run this, we get back the result was satisfied. So Z3 found a solution, and it gives us back the model where X is mapped to 1, which makes sense because that's our constraint, right? Okay. So that was the long-winded introduction to the Z3 Rust bindings. It took us about, it's 15 minutes. It's not that bad. Probably like 45 minutes. So let me copy another piece from my project over that I really like. Copy source C3 util AST verbose print streaming. Okay, now we have that, and this is basically, we'll move that into here. What I did is I wrote this function where you can kind of inspect the structure of each AST. So it will go through, for each AST, it will tell you what's the kind of AST. So like, is it a function being applied? Is it a, let's see, what were the different kinds? Is it a quantifier? So is it a for all statement or something like that? It's going to give you the sort kind, which the sort of an AST is basically the type. Again, this is a difference between how Z3 calls things and how everyone else calls things, or at least how I call things. This is the type of the expression. So this might give you back bit vector, or it might give you back Boolean, right? And if it's a function application, you can also get the declaration of the function being called with decal. And then here we do for the declaration of the function, we print out what's the name of the function, what is the type of the function, which there's a couple things. So for example, true, the value true is a function that does not take any arguments, that always evaluates to true. It's kind of circular in a way, but it makes some sense. Basically, the point is every constant in Z3 is a function with no arguments that just returns the value of the constant. And this is basically giving a name to it. And so this gives the name true to the function returning true. And so the kind for this would be the the function kind is the true function kind, then there's a false function kind. And you can also have an uninterpreted function kind, which means we don't know what the value is. And that's what how Z3 handles variables. So this would be either uninterpreted, true, false. There's some other things. Then the arity is the number of arguments it takes. So if it doesn't take any arguments, it's a constant. Or if it doesn't take any arguments and it's a function application. Then the domain, again, is the input parameters. The range is the output parameters, or like the input types. The range is the output types. And then the parameters is a description for, again, this is like kind of the same thing as domain, just in a different type, where this will tell you, hey, this function parameter is a double. This function parameter is a string. It's an AST. And then the domain tells you, hey, for that AST, it's a bit vector. It's a bit vector AST, not just any AST. And then it will print out all the children and recursively call itself. So we're going to use that to investigate our ASTs a little closer. So let's try it out. First thing we need to do is here, we're going to make it build that as part of our code, verbose print. And I'm basically going to use this code to like inspect expressions to figure out what our JIT compiler needs to do. So here, for example, if we go to, unfortunately, I have to cast it to dynamic because reasons. This is an annoying part of Rust, in my opinion, where for some reason, so an AST is defined as a trait. That means there can be different things, all of which implement the functionality of an AST. Dynamic is one that can be anything. But you can also have like a bit vector is its separate type of AST that you can always cast to a dynamic type of AST. And so a dynamic basically can have any type, and then bit vectors, strings, and such are all specializations. So I can take my dynamic, and if it is of type bit vector, I can get my bit vector specific constraint out. It's a way to make the type checking nicer. The unfortunate thing is, if I tried to implement it for everything that implements AST, somehow, which you could, because all this uses is AST specific functions that doesn't use any of the special functions that are only for specific typed ASTs, but somehow it doesn't recognize it. And if anyone knows why or how that is, feel free to let me know. I'd be interested to know. But anyways, so long story short, we have to cast it into a dynamic AST first and then print it out. And then we can call print verbose. So now if we look at that, this is just going to be our variable x. And we can kind of see what I was talking about. Okay, so x is a function application. So a function being called where the return type is bit vector. The type of the function is a function that returns a bit vector of size 8. And then the declaration for that function, the name of the function is x. The result is the kind is uninterpreted. So again, this is what we talked about earlier. Variables are uninterpreted Z3 constants. It doesn't take any parameters. The domain is obviously nothing. And then the result type is bit vector of type 8, bit vector of size 8. Okay, that kind of matches up. So now let's, instead of doing x, we can actually take this and stick it into a constraint. And then here we pass the reference to the constraint. So now if we print the entire constraint, this is going to look a little... So this is the representation of our constraint, and we can see it's just the Z3 representation of x equals 1. And so the highest level node here is an application of a function returning bool. And the function name is equals. The kind is equality, right? Because it returns whether the two things are equal. It takes two parameters. And here in our domain, we can see what the type of those parameters. So the first argument is a bit vector of type 8. The second argument is a bit vector of type 8. And then it returns a bool. And so then this AST, this node has two children. The first of which is x, which we've seen before, is function application of type bit vector. Type exactly is bit vector of size 8. Of variable x, which is uninterpreted. Or function of a function named x, and the result is uninterpreted. So Z3 can pick whatever it wants for the value. And then the other child is the constant number 1. So this is an AST that is a type numeral, also of type bit vector though. It's an AST of kind numeral. So the type of AST is numeral. The sort, or the this is a little confusing terminology now, but the type of the value is bit vector, and the actual instantiated type is a bit vector of size 8. And all that is again a function call to a function named bit vector that returns. Oh, right. Okay, I remember now. So to turn out earlier, the domain is the domain is for the input parameters of your function, and then the params is, or the parameters is basically any arguments needed for that function, if that makes sense somewhat. It doesn't quite matter. We'll get to it when we're actually jitting things. The point is this function is of type bitnum. So that just means it takes these specific arguments and then returns a bit vector. And the arguments are the constant value 1 and integer 8, because that's the size of our bit vector. Okay. Long-winded story. Basically, this is the structure that we're going to take, convert into a program, and then run on our byte inputs. This is what we're trying to JIT. And so it's nice to have it printed out like this, because then you know exactly what the different parts you have to deal with are. Okay. So let's go back to our interface. So we've established that our model specifically that we're trying to satisfy is just a list of bytes. Because we know exactly what constraints we're expecting, we can fix this to be whatever, we can specialize this to the point where we can say, hey, we can use this to make our job easier. The other thing we know is we're always going to get either true or false back. There's nothing else there. We're specifically looking for constraints. I don't care about like getting expressions out, things like that. All I care about is the constraint satisfied or not? And so both of these things are going to make your job a little easier, because we can assume a lot of things about it. So we don't, for example, have to deal with like, how do we write this function if it needs to return floats and bit vectors, and like how do we encode bit vectors, because it doesn't matter. The only thing going in is bytes. The only thing going out is bool. Everything underneath we can do with what we want. We can treat that however we want. All right. So let's take this example that we made, the x equals 1, and let's kind of think about how we would want that to look. So I'm going to get rid of the solver stuff, because I really don't care about this for this specific project. I I don't really care about the solver part because we're not going to deal with the solver, right? The solver is going to give us an input, sure, but all we care about is if we already have an input, if we have any input, does it satisfy our constraints? So let's say we had x equals 1. How would we want that to look? And so I think my first plan of action here is to just keep the JIT simple, where we're not actually going to do anything super complicated to perform optimization. So we're not going to do any like register allocation, things like that. We can do that later. What I want to do is first get a simple example working. And so the simplest way I can come up with to do that, or at least I can think of for now, is we're basically going to have, I think Rust allows new lines and string constants, right? Yes, they do. Okay. So what we would have here is we wouldn't have x, right? We would have input var of 0 because we're going to have one variable for each byte, and we're just going to take a variable. And so this is going to take, actually that's var 0 equals 1. This is the constraint before. And what we want to calculate actually is, okay, well, replace var 0 with the actual byte value, and then check check what comes out. So we're just gonna, this is kind of how I'm thinking of it in my head in terms of the actual program, is we're just gonna have a char pointer as some character buffer of like whatever size it is, however many bytes we have on our input. And that's going to hold the actual byte values. And then what we're going to do is we're going to say, okay, well, take model of 0 and then return model of 0 equals 1. Okay, well, that's not a very interesting example on its own. Let's say we wanted to have var 0 plus var 1 equal to 1. Okay, well, we would have input byte of 1 equals to 1. So now how would you do that? Now you have basically two sub-expressions. And if you think of this, we can actually rename them so that they're equivalent. Let's make another variable, var1, and we can look at how that prints out. Basically, the point is now we're getting into the tree structure because we have a left sub-expression that is actually another tree that is var0 plus var1, now returning an integer. And then we can do address x plus address of var1 plus var, that was var0, var0 plus var1 dot equals. So this is our new constraint. We're going to say var0 plus var1 equals 1. So now what that actually looks like, though, is we have, if we think of it in terms of Z3 again, we have plus, and this is one thing that's nice about the prefixed order of the operators, var0, var1, and then we have equals 1 in in very shoddy terms. So this means we need to, before we can compute the outer expression, we need to compute the inner expression. So here you'd have something like int temp0 is model of 0 plus model of 1. And then you say, now you return, and then bool temp1 is temp0 equals 1, return temp1, right? And so this now mimics the structure we have in our constraint to some degree. At least it mimics it a lot better. And so that's kind of how I'm thinking of computing these things. Now, there's two parts here that are interesting. One, let's say we have some really complicated expression, right? Like we're just going to call it expr1 is some really complicated stuff, expensive to compute. What if we now have expr1 plus expr1? So like we just take 2 times expr1, but the constraint does it with a plus. One thing we want to avoid is having this computed twice, right? Because it's really complicated, it's really expensive. We don't want to have to do it twice. We want to be able to just keep the result and reuse it the second time it comes up. And so you can think of this as almost caching results by AST ID. The way I'm thinking of it is more, we're going to have, I mean, we are basically caching the results of the AST. We're just going to have a variable for each expression being computed. And then if the expression is being used again, that we've already declared a variable for, then we don't need to do anything. We just reuse the variable twice. And the important thing for that to work is the variable, the value of each expression can never change. So that's kind of the same idea of the single static single assignment or single static assignment. I don't remember which one in compilers. Is it becomes a lot easier to reason about things when every variable is assigned to exactly once, because then you can just go back to the definition and you know exactly what its value is, and it hasn't changed in between. You don't have to deal with, well, what if it's different on this path versus this path? Okay, so let me, what was the, there was a cool tool. Was it this? No. What was the thing Fabio used? Let's try this, because then I can maybe show a couple things. Okay, so, oh God. Undo? Do you have an undo? Yes, you do. How do I change the size of the marker? Yeah, okay, that works. Make it a little bit smaller. So let's say we have our x here, right? Actually, hold on. If we take this tree that we drew earlier for the x plus y equals 1, if we think of it in terms of a tree, we would basically have our equals. Oh God, this is not the greatest, but whatever, it works. Then on the right-hand side, we just have our expression 1. And on the left-hand side, we have our expression that is And this kind of matches the representation in Z3. We have var0 and var1, right? So when things are a tree, then it's actually kind of nice because you don't actually have to deal with the variables. Once you're done with a node, you're not going to need it again. You're just going to propagate it up the tree. Now, what we have in the case of our representation is not quite the same thing. Can I just clear out the entire form? Because we can actually have a graph. And the best example of that is just the case of the expression 1 being reused twice, right? Because remember, in Z3, every AST has a specific ID. So if you reuse an AST, they're going to have the same IDs. So basically what we're going to have is we're going to have our node plus, and then on the left side, we're going to have expr1. And on the right side, we're also going to have expr1. And so in a tree, it'd be easy to just say, oh, we just start with the leaf nodes, compute them first, and then go up the tree, right? In a graph, it becomes slightly harder, but there is a very easy solution for this, and it's called topological sorting. And it basically works the way you think. It's just like, hey, start with the nodes that don't have any kids, that don't have any children, do them first, and then do everything else after. And that's why, if you remember at the beginning, one of the things I imported is pet graph, because we're going to need some graph stuff to make this work. Well, that sucked. Sorry about that. Okay, well, that didn't work. Let's see. Let's give it a second for people to rejoin. Did not mean to do that. We'll just do it in code. I'm just going to give it a second for people to get back in if they want to. Let's see. That's a shame that I can't draw, but oh well. Ooh, well. Okay, well, now we know not to try that again. Let's see what this says. Okay, somehow the viewer account isn't updating, but it looks like, on the website at least. Oh, there we go. Okay. So people are back. Okay, so that was a fail. That was 3 minutes of me talking to myself, not realizing that Zoom had killed OBS. So apologies for that. What I said in the meantime is basically, this might be one of the easier cases where you have, where the nodes being duplicated are actually at the same level. It becomes harder if you have things like expr1 plus expr1 times x_1, things like that, because now you have the top level has an instance of x_1, and then you have a level below, and then more instances. So what we're going to want for that is topologically sorting them. So basically starting with the nodes without any children and going up from there. All right, so oh, whoops, let me check that issue on the mic. Let me try. Is it better now? I did it did have the okay, perfect. Yeah, thanks for letting me know. The restarting OBS had unmuted my laptop mic, and my standalone mic was also recording, so I'm guessing that's what you heard. Okay. So, long story short, I imported a graph library specifically for this reason, because that's what we're going to need. So let's start out with that. Let's take our ASTs and produce a graph that looks like them. Let me see if petgraph actually has a way of visualizing the graph, because I think that would be a cool way of seeing it, like getting a dot file out of them. Petgraph dot, caps lock is on. Okay, yeah. Let's try that. Okay, so first goal on the list is taking the graph, taking our constraints, or a single constraint, and converting it into a graph. So I'm going to make, here we're going to call it a constraint graph, and just to keep the logic separate. We might merge them back in later, but for now, let's do this. And then we'll have a separate test case for below. But we're going to have a constraint graph. And one thing we're definitely going to want is we're going to want a way of outputting something that we can look at. And one thing I've seen that I like is you can output the graphs in dot format, which is easy to render. So let's look at this graph library. I haven't used it much myself yet. So let's see, standard graph, adjacency list, that's fine. Okay, so we have indices, identifiers. Okay, let's just mess around with it, right? As we do normally, we're just gonna mess around with it and see what happens. So let graph, pet graph, let me use pet graph so we can actually use pet graph, and then it's looks to just be, do they have usage examples? Graph. So we have a data node for nodes and an type for the edges called weights. Okay. The associated data can be of arbitrary type. Are the graph edges are directed or undirected? We're definitely going to need directed ones because we need to distinguish parents from children. And an index type, which determines the maximum size of the graph. Ooh. Oh, no, okay, yeah, we can just make that U128 or something. We don't actually care. Okay, so we're going to take a graph where I think the first parameter is the nodes. Yeah, nodes edge as type equals directed, index is default index. Okay, that's fine. Let's make a graph node. So we're going to call it AST node because that's what it is. We're going to give it, let's give it we might actually just be able to stick the ASTs in there straight up. Let's make a wrapper. We can actually make it take. So each AST node has a reference to the AST it belongs to, right? Let's try that. We might not want that to be a reference later. We might actually just, because they're so cheap to clone, let's just stick the thing in. We'll just have a dynamic AST. What do you not like about the name AST? Oh. I was missing a step. Struct AST node. It's going to have an AST, and then let's say it also has a label. Actually, we don't even need that. All we need to do then is we can say, I'm guessing when it renders it to dot, because I do care about that. I do want that. I want to be able to look at the graph in visual form and see that it looks the way I'm expecting. Label equals A. Okay, so they have to implement the display. That makes sense. Node initial graph prop. Node weights and edge weights have to implement. Okay, they have to implement display. That's fine. We can. So in that case, we need to use standard format display. Let's implement debug too while we're at it. Okay, so we're going to implement display for our AST nodes. Actually, let's keep it simple for now, because I think I already implemented display for the ASTs themselves. So let me try this out of curiosity. So if each node is, here's what I'm going to do. I'm going to make each node just be the AST itself. And then each edge, we're just going to have an index which child it is. So like if it's the first child, it gets index 0. If it's the second child, it gets index 2. Very simple, right? Like we're just going to do this stupid, very stupid. You know what's to like about that? Expected semicolon. Why would you expect a semicolon here? That makes no sense. Cargo check. Okay, no, the IDE is just behind, I guess. And then I think we just add nodes, yeah. We might actually be able to just, oh, that's what it was. It was way up there. So we're just going to add the nodes. Do you like this or do you not like this? Yeah, okay, that's fine. So our constraint is var0 plus var1 equals 1. All right, so if we want the nodes, we need that as a separate one as well. And so the first nodes we're going to add are the leaf nodes, right? So we're going to have 1. we're gonna have var 0. We're gonna have var 1. Graph.node add, which is the result of adding the two variables. And then last but not least, we have our actual constraint node, which is constraint. Okay. We're probably going to have to do into on all of these because so that they switch into the typed in. So we get the dynamic version of them. Okay. And graph.extend with edges. We're going to add edges, and that works. Okay, just a list of tuples. So I'm basically just hard coding manually the graph I want to see at the end. So from, we're going to have a node. So if this is 0, 1, 2, 3, the add is going to have a node to 1, and it's also going to have a node to 2 because we're adding var 0 and var 1. And then 4 is going to have a node to an edge to 3 because we're adding the result of this add. We're comparing the result of this add to the constant 1. And so 4 is also going to have a node to the first constraint. Okay, I think that's that. So, and then now we need to print it. Wait, how do I get weights? Graph, extend with edges, extend with edges. Okay. Node weights are set to default values. Edge weights may be specified in the list or they are filled with default values. Oh, because the edge type itself is the weight. Okay, so we're going to have to change that slightly, but that's fine. It doesn't matter for now. This should work. So what this should do is it should print us out. If we do cargo test dash dash, another dash dash, I forgot. Is it dash dash show output? Does it work here too? That was the recommendation earlier. It is. Oh, and we need to make sure that that module is defined so that it actually gets compiled as well. Mod constraint graph. Okay, now we're missing a bunch of things. Something failed. AST verbose print. What do you not like about it? File not found. What? Oh. I'm slightly confused. What's wrong with this? Oh, that's what I compiled earlier too. It's not a comparison operator. Hello? Am I confused or is Rust confused? I feel like Rust's confused here. Oh, fuck, I forgot. So I actually need this to specify generics. I forgot. Alrighty, so we have our graph. Let's see, what do you not like about this? Trait default is not implemented for dynamic. Oh, okay. What we can do then is we're going to make this an option of dynamic. It shouldn't ever trigger because we've added all the nodes first. I do like this part where you can just type at the end and it makes it into an expression for you. Here's your pseudocode. It's kind of nice sometimes. Didn't do it there. There you go. Come on. There you go. So then this is going to be config from pet graph. This is going to be dot from pet graph. Are you cool now? No, cannot borrow is mutable because I forgot to declare it as mutable. Glory of Rust. Okay, so we have our dot here. And we can actually, just for now, let me just dump it into a file manually. Test dot. And then we can look at it. Look if it looks the way we're expecting. Oh, unexpected end of file. Okay, yeah. So some var 0, some var 1, bv add var 0, var 1, and then we're comparing them for equality. Makes sense. Okay, so we don't want to print out every part of the constraint each time. What we're going to want to do is we're going to make custom types for it and only extract the parts that we need for each layer. So like we're going to take, is it a function application? If so, what are the operands? Things like that. But that works for now. So the other thing we want to do is, let's say instead of var 0 plus var 1, we had var 0 plus var 1 plus var 0, right? Oh, that's unfortunate. I don't know if pet graph allows for multiple edges from the same node to the same node. Pet graph multi-edge. We might have to implement that ourselves. Or duplicated edges. Oh, graph does allow parallel edges. Adds an edge from A to B to the graph with its associated data weight. Return the index of the new edge. Computes an O of 1 time. Panics if the nodes don't exist. Panics if the graph has the maximum number of nodes. Graph allows adding duplicate edges. If you want to avoid this, use update edge. No, I want that. I want that. Okay. So let's say our constraint instead was add 2, add var 0. So we're adding var 0 twice. And then here we'd have add 2 dot equals 1. Oh, that should be plus. We also don't need these parentheses anymore, since they're now all separate sub-expressions. Add 2 equals 1. So 2. So we're going to want a reference from, so this part stays the same because add is still going to be var 0 plus var 1. Now add 2, which is node 4, is now going to be node 3 plus node 1, I think, because that's var 0, right? We added var 0 again. Yeah. That, and then node 5 is going to be node 3 plus node 4. Okay, I promise we're about done with doing it manually. So, but I think it's good to know kind of what you want to see at the end, and then you have something to go for and compare against. Oh fuck, I can't copy out of this. Do the Control-Shift-C thing. Let's render that again. Interesting. So now we lost something. Let me find out what that was. var0 plus var1 plus var0 equals 1. Oh, I made it compare add against add2. What I wanted is add2 against 1, of course. Stupid indices. Shift-C. There we go. So now if we render this again, now it should look correct. Yeah, so now we have var0 plus var1. And so it looks like actually Z3 compressed this into being one add statement. So we'll get to that later. But this works for now. So we're going to have equality. Our comparison here is comparing 1 against the triple addition. The triple addition takes add2, which adds var0 and var1, and then adds var0 again. And so this is where we can actually see in the I should have just done this for the visualization earlier. This is way nicer. You can see here we're going to have a graph. We're unfortunately not going to have a tree. But the benefit of that is because we're going to have it in a graph, it's going to make it very easy to tell which results we're going to reuse, which is going to be important down the line. All right. So let's build this graph, shall we? So first things first. We're going to need, and this is going to make it unhashable, but I don't care. Hash map. So our graph is going to have a node to index mapping. Actually, can we get the node for each index? Node weight. Access the weight for node A. Oh, does add node return the index? It does. Okay, I see. So we're actually going to need the opposite mapping. Given an AST, we're going to want to find for the AST which index in the node it is. Like which index in the graph it is. Filter, blah, 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 blah. We're way too low. I want here. Go from here. There's references to nodes and edges, but these are only stable across certain operations. Adding nodes or edges keeps indices stable. Removing nodes or edges may shift other indices. Oh God, are you telling me they're not using generational indices? Oh no. Why would you not have a generational index so that you could catch that? Oh, that's annoying. Oh well. So what happens if the node already exists? Well, nothing better than to try it out. Actually, out of curiosity, does the graph have a debug implementation? Like, can I just print the graph? What does that do? Please tell me it does. That would suck if it didn't. Node to index. Okay, yeah, we can get rid of that for now. Oh, thank God it does. Okay, so we have 6 nodes, 6 edges. We have some node weights. So what happens if I try to duplicate this node? Like, let's duplicate this one. Let's just add it twice. What do I get? Oh, damn it. Okay, so you can add the same node twice. That's slightly more inconvenient. If there's an update edge, is there an update node? I don't see it. That's a shame. That's a slight shame. Retain nodes. Ooh, I like this. I like that we can map and filter across the graph. I like that a lot. That's cool. That's very cool. Actually, let me go to the latest version, please. Undirected with capacity, edge count is directed at node weight. Okay, so given a, so we're gonna have to keep track of which. That's fine, I can do that. We're just gonna have to keep track of which. Directed edges. How's there no find node? What were they thinking? I guess I could look at that, but. Okay, so we're gonna have to keep track of the mapping of which index our ASTs are in our graph ourselves. That's fine. That's fine. We can do that. All right. So, AST to index is going to be a hash map mapping from. Okay, we'll just stick the entire AST in. Dynamic to usize. What if I made generational indices? But then no, I'd have to mess with the thing internally. AST to index. I could. I might. You know what? Let's do this. Struct node index. And then we'll do that. That way we have the option later. We need to import UFU, of course. This is going to be context because we're going to, again, here we're basically saying this AST object of type dynamic, the context has to live at least as long as this object does. The lifetime of this object has to be shorter than the one of the context, which, as we've explained before, because every AST belongs to a context, that's kind of the requirement we're saying here. And then we're going to have our graph, of course. So we're going to have a graph here. We'll end up probably specializing. We'll probably end up having specific node and edge types, but for now, I'm just going to keep it as it is. Node type is dynamic, and then edge type is just an index. Okay, we need to import graph. Sorry, give me 1 second. I will be back in 2 seconds. All right, we're back. Sorry. So, yes, and because we have the AST, when we're looking for one, we can actually know which ID the children are. So we don't actually have to care. What I might actually do is so that if I pass the object directly, basically both the graph and the hash map are going to take ownership of it, which means I would have to clone it each time. Do I want that? Or do I want to just take the hash ID of the constraint and stick it here? Let's leave it for now. Overthinking. So first things first, we're going to make a constructor for it. And that's going to return a constraint graph. And I think we might just be able to do this, because I think hash map and graph both have default fillers. Okay, they do not have a default. Let's check why not. I'm guessing it's the graph's fault probably, because I know. Oh, I forgot the lifetime, of course. Okay, our constraint graph. Okay, now we're gonna have, it's not implemented for constraint graph. Can I derive it? Default, debug, clone. You can't clone a hash map? What? Oh. Of course, I have to do the same thing here. This thing is also copyable. Let's see. What do you not like now? Dynamic re-imported here. Okay, get rid of that one then. Okay, I'll deal with you guys later. I don't want to remove things that I'm going to end up using anyways. Okay. So we have our new. Let's see that we're also going to have. Let's see, function. We're going to make a function dump, and that's going to take a file name. Stir. Standard. What is it? I can never remember. What does this do? Never seen this before. Just out of curiosity. Oh, that's cool. Huh. FS, right. Isn't there a right to file? Okay. Rust, right to file. Don't want to do that. It has to be. It's read to string. Oh, it's just FS right. Okay. FS right to the file name. We're gonna write our own debug representation for no, we want to write the dot file contents. Assert file name dot ends with dot dot. Don't tell me you don't have ends with. You have starts with, don't you? Oh, it's with an underscore. Is this a reference or something? Oh. Too much Python to single quotes and double quotes are not my forte anymore. And we're just gonna want this. And we might add edge labels later. What other things can we configure here? Edge no label, graph content only, node index label, node no label. What's node index label? Use indices for node labels. Nah. Let's just dump it normally. What's wrong with this? With config. And then we print out its debug representation, I guess. Content. I'm guessing we might have to reference this out. Self dot. Oh, I didn't define this as a self. Graph. Nice. Okay, then here, expect, why can't I write? I guess we can just return the results. Yeah, I don't care. Okay, cool. So let's actually try that out. Function test empty. Graph equals, we'll make a new constraint graph. Graph.dump empty dot dot. Okay, let's run it. Both tests passed. Tested works. It works. Oh, I need this to actually declare that a test as well. I don't actually want to see the output right now. Okay, now it ran. Let's see what it looks like. Oh, I called it empty dot dot. My bad. Oh, here it is. Okay, I mean, it's empty, so that makes sense. So what we're going to do here actually is we're going to make this just straight up take the constraint. And we're not going to call this new. We're going to call this for constraint. And then this is going to be a bool to make sure that we're getting what we're expecting. Okay, so because we derived default, that means we can just create a constraint graph with default arguments, which is just an empty hash map and an empty graph. If we just do this. So let's do that. So this gives us our graph. And we're going to want that to be mutable. Because we're going to have to borrow graph mutably to add in insert nodes. The same with the hash map if we want to insert things. We're going to need to do that as well. Are you not imported? It's not. What's wrong with you? Oh, sure. Here, just return that. How about? So that you're happy. So, because, yes, let's keep it like that for now. So, we're going to have, because we're going to have to process multiple children and like do them in order and things like that, we're going to just do a normal to-do list type deal. Yeah, you don't know what the type is yet, but that's fine. Actually, I guess we can just define it. You're going to be a vec of type dynamic. We're going to push our constraint dot into to convert it to the dynamic version. Need to declare you as mutable. Okay, while to do. While let x equals to do dot pop. I do like this part. So here I can just say while there's still something in the to-do list, basically. We're gonna see. Thank you, Cat, for walking over my keyboard. Unfortunately, there's no webcam, so you can't see him just like waltzing across my keyboard. If self.ast2index, oh, it's index.contains. Wait, what do you not like? Okay. If graph.ast2index contains x, An expression cannot be a sub-expression of itself, right? In no way. No, there's no way. Yeah, we're gonna say there's no way. We're just gonna continue. Why do you need type annotations? What if I define that needs type annotations? Cargo check. Oh my god. Of course. Let's take a reference. No? Oh. Okay, if it contains the key, return it straight up. Otherwise, let graph index is graph.addNode. Oh, I guess I have to do this now. Add node X. And then here we're going to insert. Actually, we're going to. Again, this is the thing where both data structures take ownership, so I'm just going to clone them for now. Or we might actually have that, just want to have that be references or indices later. But for now, that should be fine. X, G index. Oh, it's the. My bad. Sure. Wait, why would that be U32? So X. Expected type suit size. What is this node index if it's not the same thing? I guess I imported the wrong one. Is that what happened? ModRS. Is it graph info? this it? Well, how do you expect me to use that if you're not going to let me get it out? PG. Well, I can't type it if you're in a private module, so how about we go here and you show me what you have in your lib.rs. Graph, simple, node index. Oh, use pet graph. Maybe that's it. That would make more sense. Come on. Okay. There we go. Maybe you're going to like that one a little better. Node index. Don't need you. Did I redefine node index or something? No, that's the right thing. Found struct of U32. Oh, is it because I didn't? Oh my god. Okay, fine. Tie undirected usize. I want the indices into the graph to be usize. Okay, now you, okay. Okay, so it defaults to a U32 for the index into the graph. That's nonsense. We don't want that. Okay, that worked. Sorry, that was a derp on my part. Okay, so insert it into the node, and then we do X in. Let's actually do that first. First, we're gonna do children or something. Yes. To do dot push. See? Like give back a back? It does. So we can just do to do dot extend, or actually do to do dot append. We pass a reference, mutable reference to the returned vector, and then we get that. So that way it takes the vector returned here and appends it to the to-do list. I think that might just be it. So we added to the graph, we added to our mapping. Fine. So now here we're still gonna add our new again because it was kind of nice to have. Strain graph. Of course, we need to define the lifetime again, and we just do the same thing. Default, default. I will say one thing I like about Rust, if you didn't notice yet, there's the default return. Like if you just, whatever the last statement is in the block gets returned, it's kind of nice. So like this here is equivalent to just return graph. Kind of like it, not gonna lie, not gonna lie. I'm a fan. Okay, so now what we can do here is we're gonna say here, okay, what is the graph we've actually built? 5450, okay. So we're gonna do fs right expected we'll check that our graphs are actually the same. So here, we expect this to be the same. We're going to format this. This is the expected representation. Dot expect. Right, you ass. And now we make a new constraint graph. We should probably call that from constraint. And we're gonna pass it the constraint. Actual ... So now hopefully these should actually match. What do you not like? Where was it moved? Oh, it was moved here. So we'll give it a quick clone here. That should work. Cargo test. Let's see what we get. So in this terminal, we're going to look at our expected. That's what we had before. That is not expected, I don't think. What happened here? The constraint is add 2 equals 1. Oh, I forgot we did this. So we're gonna kill that. Oh, nope. Nope. Forgot we added the extra one that messed with our indices. There we go. We have the equality condition 1, var 0 plus var 1 plus var 0, var 0 plus var 1. Okay, that's the expected. And what do we actually get back? Actually, I think we might get extra edge labels, but okay, we forgot the edges. That is, of course, not great. We're gonna need some edges here. Whoops. That is, of course, an important thing. Okay, so we added the node here. And then here we're going to say for y in okay, I think we're actually going to go back to doing this the other way. In x.children, we're gonna push a clone of the child to be handled later. And then here's what we're actually going to do. We're going to use the fancy iterator stuff. So we're going to take the children, turn them into an iterator. And then for each child, keep that here. For each child, we're going to oh. Ooh. We actually kind of do want to do this recursively, now that I think about it. Because I forgot, we don't... Here, we might not have a node in the graph for a child yet. So we kind of have to ensure that that's there first before we do anything else. The easiest way to do that. Honestly, it might just be easiest to implement a topological iterator for the constraint tree, where basically, or constraint graph, if you will, because we can have duplicate nodes, right? But we return the children first. Let's try it. Trait topological iteration function iterate or order, something like that. No. Nodes. Sure. We could just make this an actual iterator implementation, but that's a little annoying. Fuck it, we'll do the ugly version that's probably slow first, where we return vectors. And then later we can turn this into an actual iterator. When we want it to be efficient, but for now I don't care. Okay. Should we do an iterator? What do you guys think? Let me know if you want me to do the iterator immediately. Let's see. Nodes. I'm gonna do that. Context. Topological iteration. Or call it topological sort. It's a little ugly of a name, but it works. Topologically sorted nodes for dynamic. Like I said, unless someone really wants me to do the iterator version, we're gonna do it this way. And if so, let me know in chat. Okay. So first things first, let's just do this for now. So the compiler stops complaining. Yeah, no, I don't see that being a problem. Let iter equals into iter. For child in self dot children. Iter dot chain. Child topologically sorted nodes dot into iter. What do you not like about that? Why do you not like that? Sorted nodes. No, that's a vector of dynamic. Okay. Let's actually just do this. And then we do child nodes. Why can't you just take ownership? I don't understand. Why is there no append function that just takes ownership of another vector and just sticks it at the end? Like, I don't understand. This does not seem too hard. Why do I have to make a mutable reference and then throw away the object myself? Just seems kind of silly. Anyways. So once all the children are processed, iter.push self.clone. We probably shouldn't call that iter anymore since it's no longer an iterator. Push ourselves at the end. Unique. I did want to do this. What was the other thing? I wanted to, what's it called? Iter tools? Use iter tools? Is it? I might have to actually import that. Iter tools. Is it that? I think it might be that. Yeah. So that's 0.10.3. Use iter tools. Iter tools? Is that good enough? Oh, we don't want a reference here anymore. Yeah. Okay. So this is slightly expensive, but it should be fine. This is not a great way of doing it, but it works. So now we can actually throw this entire thing away because now we can just say for a node in constraint.topologically sorted nodes. Now we know that all of the children are going to exist. And we have also ensured via this unique that we're not going to have duplicates. So what we can actually just do, we can throw this shit away. We can actually just say that we should never see this because otherwise our function is wrong. not this should never contain our node. We'll call this from constraints. Okay. We had to convert the bool into a dynamic for that to work. That's what I just added. That's fine. Cargo, I did not want cargo test, I just want cargo check. We don't need the to-do list anymore. So this actually ends up making this part of the code a lot nicer, funnily enough. Constraint dynamic, actually I can just do this. Constraint dot into, and then declare this to be if type dynamic. Boom. Problem solved. I don't need you anymore. I've already handled that part. So we know that's not the case. We know that it's never going to contain the key. So now we're going to look up the indices. Children.intuiter, and we're going to map each child to instead look up the index in graph dot AST to index dot get child dot unwrap, because we always expect them to exist. Expect how are topologically how are children not yet in there if this is supposed to be topologically sorted. A little long, a little annoying, but you know, we do what we do. Okay. And that into a vec. All right, so now we have our indices. Why does this give a reference? I'm slightly confused. What's the entire type? Can I get a copy of this, please? It's a node index. You should be able to copy node indices, I think. Let's see. And so this is going to be node.children. Okay. So now we have our child indices. We're going to add ourselves. Yeah, I should do this up here. First, we add ourselves. Okay, we're just gonna do this because it's funny. There's no real reason to do this, but we're gonna do it anyways. Because realistically, what I should have just done in this index is that graph dot insert add edge update edge. We don't want duplicate edges from that, I don't think. Do we? I don't think we do. Let me think about this for a second. Do I want... So every edge is supposed to have the index Let me think about this for a quick second. Update edge. Okay, I can set a weight. The index of the affected. Add or update an edge from A to B. I think that's fine. So we're gonna call that my index. I think there's gonna be a problem. Could just do it at the end because I think everything else just works with the references. Let's do this at the... Okay, we'll do this at the beginning and then we'll add ourselves into the dict at the end so that the dict can take ownership. Because we're already cloning it here. I don't really want to clone it again, but I need the index. So we're going to do this. So there's going to be node.clone. I'm just going to abuse the hit count. I'm going to abuse the edge weight to be the index of the node for now. And then we can decide to change that later to be of actual struct value so we can store information about like edges. I don't think we're going to need to. So we're not going to. So we're going to add my index to the child index with weight. We're actually going to do enumerate here. Index. Then this is going to have to be a tuple because that's how enumerate works. And then this is the child graph index to avoid confusion. So we're going to add from my and then let's rename this guy my graph index. And then the weight is going to be the child index. So this is going to be the how many the nth child, if you will. And then dot drop or something, I think. Actually, I don't think I need to do that. We can actually just do this. For node in, we're going to go all the way back to normal. Constraint.children.enumerate. We'll throw this stuff away. We're going to throw all of this stuff away. And then this is going to be child node. This is going to be child index child. All right. That was a long one, but I think that should do it. If I'm not mistaken. Enumerate. Okay, find into iter here, and that way we can enumerate. So now this is going to be constraint.clone. And no, this is right. I just copy pasted this into the wrong place. For each node, we're going to add ourselves to the graph. We're going to check that we're not already in the graph first, hopefully, because otherwise this is going to be very stupid assert. We're going to add ourselves to the graph. We're going to iterate through all the children, add each of them to the graph. Let me put this here. I'm going to add each of them to the graph. And then we're going to insert the thing into the hash map with the corresponding index. Okay. Let's see if that compiles. Probably not. Cannot borrow is mutable. Cannot borrow child nodes as mutable. Why not? Oh. Even easier. Okay. Let's see what it does. Let's see if it worked. For constraint. Yes, I renamed that. I am dumb. That is now from constraint. Oof. That's not great. Okay, so we fucked something up. Somehow, expressions are getting returned multiple times. Let's see. Why? Let's do a quick thing first. Every time we call topologically sorted, let's do that. Print topo sort of equals that. This is going to be verbose, but it's going to be fine. Self is result. Result. Okay. Oh, actually, I do want. Okay. So we're going to descend all the way. Down into var0, var1. We're going to have, this is going to return var0, then var1, then the combined AST. Okay, that's fine. We're going to descend into var0 again, which ideally we would catch, but whatever. var0, var1, var0 is var0, var1, the added expression, and then the triple add. Yeah, var0, var1, bv add var0, var1, bv add var0. The triple add, the node 1, and then the triple add equals 1. All of those are individually unique. Oh, I'm dumb. I don't want it to contain the key. Ouch. Ouch, ouch, ouch. Okay. That's not great either. Okay. Let's just be very verbose in what we're printing out. We just inserted node. Just for the purpose of printing here, let's just do that real quick. I guess we can just do that. Node rubber is format. Node rubber graph. Print line inserting node. Are you a vampire? I do. Because I can't see your face. Yeah, unfortunately my webcam is not working. I figured this out too late. I can't even blame Linux this time because Windows doesn't find it either. Yeah, it's very helpful on the floor of DEF CON. Indeed. Hard rejected by the hardware. All right. Let's see. What does this do? Nope. Semicolons are helpful. I should make a 404 Lucas not found image to put on Zoom calls. Oh, I'm so dumb. Of course, this has to be node.children. There we go. Come on. Hey, it works. Now let's look at this graph. Okay. Okay. I can live with that. I can live with that. And to double check. I didn't have the weights in the other one, but looks pretty good to me. That looks pretty good to me. Yeah, no, we don't even need the default nonsense with the option, which doesn't make any sense. Didn't make any sense in the first place. So that's good. That is good. Cool. So funnily enough, I don't know why that keeps happening, unfortunately. Well, hopefully. Good point. Okay, so the mic should be fixed again. How long was I gone for? Because I did not realize that the OBS had crashed again. I'm gonna need to do something about that. Damn it. Well, that sucks. Yeah, I'll have to figure out why that keeps happening. I'm not sure. Unfortunately, I'm not sure why that keeps happening. Well, good thing that the title is failing to write a JIT compiler, because failing to stream about writing a JIT compiler too, but you know. Okay, let's see. So in the meantime, what I was doing was trying to figure out if it makes any sense to use some kind of Rust binding for LLVM to do this instead. Or at least to handle the types and the JITting for me. It doesn't seem super hard. If you use, there's a LLVM binding called inkwell that looks kind of nice. Where it looks like all you do is you define your basic blocks, which, other than if we have if then else constructs, for the most parts, we don't have basic blocks. Where if we wanted to, we could have if then else constructs. What we could do is lazily evaluate only the branch that is actually taken. That might not be bad. Function. Define a function type. An N64 type. Built into add. And we return the function. This actually looks pretty nice. Not gonna lie. This looks pretty easy. Okay, I might give that a try. And then you just do sum.call in an unsafe block to get your results. That might actually be worth doing. Then the only thing we need to do is map our values to map our Z3 types to LLVM values, and then LLVM will do everything for us. Okay, yeah. Let's give it a try. Why not? Let's give it a try. So in that case, I need to install inkwell. Makes sense to add different basic blocks. Yeah. Okay. Whoops. Inkwell. Let's see. What are we at version wise? Ooh, that's not great. Oof. Version 0.0.0. I have lots of trust that this is well maintained. But I guess we're supposed to install it from Git, so. Let me actually check what version of LLVM I have available on my system. Sudo apt search LLVM. Let me put up a h-stop on the other screen just to get an idea of if maybe OBS is running out of memory or something, so I can get an idea of why it happens next time. Oops, not that. Damn it. Okay. Let's see, which version do we have? LLVM 9, LLVM 8, and 6, 7, 12. Okay, so we have 12. So we'll use 12, I guess. Doesn't make much sense not to use the most recent one, I don't think. Let me put you up here. Default seems to be 10, but I think we're going to go with 12 here. That makes sense to me. So let's give this a try. So we're going to have our topologically sorted nodes. Let's just do a function test where we can kind of like mess around. Context is inkwell. Oh, I need to. JIT constraint. Mod JIT constraint. There you go. Now that should compile. Oh, if the stream drops again, just in case, ping me in the chat so I see, because I might notice that where I might not notice OBS going down if it's not on screen. Honestly wondering if it's not like Rust compiler taking up so many resources that OBS decides to die, which would suck, but let's go back to here. Okay. Let's copy you. Straight up copy paste programming like a good programmer. More copy paste down here. We're going to copy the code gen struct because we want that pretty much the exact same way. We're going to add this. We're going to make this JIT compile constraint. Okay, the mic is back on. So I had to mute because I had to sneeze. Okay. So here, I'm wondering if we should just have each constraint be a function. Like each node in the AST be a function, and then just let it inline aggressively. That might actually work. That might work well too. Is there a way to disassemble in Rust? Rust disassemble. Is there no new? How do you construct this thing? Yeah, but how do I use you? Hello? Okay, well, fuck it. We're just gonna look at this. What's good. Well, saying it's fully documented is a strong statement for this. I might just do. Friend Alex, he's gonna be very happy about this. No, come on. There has to be Rust capstone bindings or something. I can't imagine. Okay, yeah, there we go. 6 codes. $164. Ugh, absolutely not doing that one. Do want detail. Do we want detail? I think we just want to print it out. I can also just like attach with the debugger. Hold on. Okay, yeah, we have options of looking at the compiled code that we can use. So cool. So if we compile a single AST, then this is not going to be a sum func. What did they define the sum func as? What was it? What is this? There's a different set of bindings. Okay, no, I want the other one. I want to build the LLVM IR. I don't want to just read it. Okay, so here's what we're going to have. We're going to say type JIT constraint. And what that's going to take is it's going to take a it's going to take a normal U8 pointer. It's going to return bool at the very end. Why do you not like this? Oh, it's going to take a const U8 pointer. And it's going to provide bool. And I'm not going to do any checking on the size because I don't see a reason to. Because we're building the constraint. We know how many variables we're expecting. We know how long we expect the input to be. So I don't really see a reason to mess with size checks. That'd be a fuck up on my part. And I guess we could. Ah, fuck it. We'll pass the size. Why not? Do size. Okay. Let's make that I64. Let byte type self.context dot. What types do we have? Constring construct. Floats by ints. Pointer sized int type. Void type. Pointer value. Okay, we add the function. Okay. I'm more interested in figuring out how I can pass an array type. LLVM context array type. Or pointer type probably. LLVM type, pointer type. But if I try to just do that, can you locate this? Okay, so you pick your normal type. You pick your type and then you make it a pointer. Okay, that we can do. Byte type is self.context.u8 type. Let buff type self dot is byte type dot pointer type. Address space, and we need what? Global, sure. Generic. What do those do? Let us see that. LLVM pointer address space. It was actually kind of fun. This is the first time I get to mess around with LLVM. So address space. An address space is a fundamental part of the type of pointer value. Pointer must have a fixed sized integral value. The null pointer has a bit value of 0. Interesting. It's always illegal. Okay. I think we just go with generic. I don't shared? No. It might be const address space const. Does that mean it's not modifiable? Address space 0 default, address space constant, attributes. Is located in a constant non-modifiable memory region is available. Sure, why not? Address space const. Element type dot into int type. Okay. So now we have our char pointer type, and then we need a bool type. Is self.context.bool type. So now we need a function of type that returns a bool, and it takes a buff type and an I64 type for the size. And it's not a vargs function. Okay. So now we need to give that thing a name. Since we're only doing one for now, let's just in fact call it sum. We'll deal with it later if we actually want to do multiple functions, we will. Name and type it has the value, blah 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 blah. Okay. Adds it to the module and returns it. Okay. So this is gonna return a JIT constraint func, not a sum func. Cool. So now we added that, we add the basic block entry, and we go to the end of that. Nth param. What does this do? LLVM build add. What do you do, mister? LLVM build add. Instruction builders. Okay, so this builds the instruction add and then does what? Does it give it back? Okay, so we might actually want to do this slightly differently. Because now we're at the stage where we're building the things. So one thing I might want to consider is, what do I want to do with if then else nodes? Because if I flip them, then I can make them a conditional node, like a guarded constraint language node, where we basically say, instead of saying we have this value is this if condition is true, otherwise the value is X if condition is true, otherwise Y, we can say we have two statements. One is value equals X, guarded by the condition. The other one is value equals Y, guarded by the inverse condition. And that way we would have the dependency tracking correct for if we want to do it lazily, so that we only have to compute one side of the constraint. But even better, actually, if I have here a, so let me see. If I do self.builder dot address space cast build assign. LLVM assignment build. Don't need this. I don't need a parser, since I already have that. I need a translator, if you will. So I might actually just need the code generation chapter. Okay. Virtual code generation in each AST class. Okay. LLVM value object. If the instruction re-executes. Okay, there's no way to change an SSA value. That's exactly what we want. I do want the visitor pattern version of it. So we're going to do that. But I actually think this might actually be quite nice. Code for expression nodes is very straightforward. Okay. Oh, even better. Okay, so what is the value equivalent in inkwell? Value. If I were to import that from, go to int value, values, generic value. So let's try something here. So if we're going to say, JIT compile me a constraint, right? Does it make sense to aggressively inline? No, let's just stick with one constraint for now. What we're going to want is, we're going to want the basic block entry. We're going to have another function here that says function JIT compile AST node. And then this takes a bool as before. and it will. So what we're going to do is we're going to hand the constraint to build down and say, you build this. Here's a set of JITted values that you can use already that we've already computed. And we're going to make that a hash map mapping from I'm going to do this again. We could do the hashes again, but we're not going to. We're going to map from that to a value. That's not going to fly. And what we're going to do is we're going to go to int value. Does have a value. Why can't I find that? Is it not public? Are you shitting me? You can't be serious. So it does have a value. Why can't I do that? Inkwell. Values. Oh, what's an any value? Is that what I want? Defines any struct wrapping an LLVM value. Basic value. Sure, we want any value. Why the fuck not? Okay. So, we map that to an any value. We're gonna have to change. Now we're gonna have to. Now we're gonna be handling two contexts, one for Z3 and one for LLVM. Z3 context, LLVM context. Still alive, right? Didn't die again. Okay, good. So I'm going to start taking that nomenclature everywhere. Okay. Let's do that for now, I guess. Okay. So I'm going to take ownership of the JIT values list and then give it back after it's been updated. And that is all we'll do, I think. Do we need to return anything else? Not that I can think of at the moment. No, I don't think so. And so basically the goal here is to have LLVM deal with all the optimization for us and to just give the JIT values, have that be the representation of each value, like the as the identifier for the SSA register, or the SSA variable that holds the result of that value, and then LLVM can figure out which stuff needs to be recomputed and how. Okay. So for now, let's just return JIT values. Oh God. So we're gonna need the Z3 lifetime. We're gonna need the LLVM. And this, the cogen lifetime is gonna be the LLVM context lifetime. And this is gonna be the Z3 context lifetime. Ooh. Might honestly just make a struct for it to deal with it for us. But for now, that's fine. Okay. So the other thing we're gonna need is, so what do you think about this? So the builder, we're probably just gonna make one basic block for each AST node. And then LLVM can deal with merging them back into one if they're just linearly connected. If not, it's not my problem. Append basic block. And then it builds a return value. Return instruction. So the other thing is, I don't want to make a function for each type because, yeah, no, that doesn't make any sense. That does not make any sense. So we're going to have to make, how do I link basic blocks? Block dot move after. LLVM append basic block in context. Wait, didn't they have a version of this? Oh, this uses iron LLVM. The fuck is iron LLVM? I want to parse. Code generation, we will use one module. Okay. What module new? LLVM value ref. Is that the same thing as? I believe it is, but LLVM value ref. Oh, so we can just keep value refs. That way we don't have to do the weird LLVM. constant. Okay, so sorry, I got a little distracted there. Don't care about the lexer. Don't care about the expression. Don't care about the parser either. Where's the interesting parts? Where's the jitter? Where do be the jitter? Okay, here, compiler. Here we go. So we have a context, we have a builder, we have a pass manager, we have a module, we have a function. We have variables mapping strings to pointer values. We have function values. Don't know why. So get a function, give it its name. Return the function value representing the function being compiled. New stack allocation option. Value. Get first basic block that unwrap. The end of the entry. Okay, so here it allocates stuff for a float 64. And here we're compiling an expression. Cool. So if we're compiling one expression that's just a number, we just return a constant float. Sure. If we compile a variable, we check does it already exist. If so, it builds a load statement and then loads the float value that's loaded there. A var in statement. Let me read the kaleidoscope tutorial real quick so I can. Introduction. Okay, what's the var in? We have these variables with this function body. Oh, is that like a new scope? Compare the initial values. Otherwise, we wet them to 0. Okay, so they have it slightly easier because they seem to only have float types, which is fine. We're just going to have it a little more complicated than that because we're going to need different types. And then operations are handled like that. If it's a variable, you get the name. Oh, right, because you get the name of the variable being assigned to. You compile the expression. And you store into the thing undefined variable. Oh, that's otherwise you get an error back. And then you store into it. Okay. So here you compile expressions for each. Oh, this is cool. So build float add, build float sub, build float mul, unsigned int to float. Oh, I guess even their comparison are floating points. The result of their comparison is still floating point. That's funny. Okay, and then if we have any custom operator, so if we have any operator that's not in this list, we check, does that function exist? If so, we're going to make a call. Otherwise, yeah, we're not going to make that call. If we have a call expression itself, ourselves. This is cool. Okay, so if we wanted to have subfunctions for our if-then-else conditions, we could have functions for those. The downside would be that we would have to recompute results inside of them if we... Yeah, I don't think I want to do that. I don't think that makes much sense. I think what we'll just do is we'll just have the conditional create the if-then-else branch, and we'll have it all in the same function. So we're not going to have any calls. Here, if you have a conditional expression, okay. Create condition by comparing without 0 and returning an int. Compare if it's 1. You append a basic block for each. I'm slightly confused how their basic block labeling works, because they seem to just append basic blocks with the same names if you have multiple conditional expressions. I'm guessing they must be like indexed by the parent expression as well. But oh man, this is so cool. We build the if then else consequence. Where does that come from? If condition, then consequence, else alternative. Okay. Continuation basic block. Okay, so here we're building the then part, then part of the statement, and branch back to the. I wonder how they're dealing with phi nodes. Let me see if they have something about this structure. If v then 0. Okay, yeah, so they do return values. I'm sorry if you can hear the cuckoo clock in the back. It's pretty loud. Then 0, else not out right hand side. Okay, so that branches back to the continuation. The then basic block. Get insert block. What does that do? Self.context.get insert block. What do you do? Okay. Prepend a basic block. Data node, kind ID. No, I want more about the basic blocks. Give me more. And okay, so here you can build structures. Okay, let me take a quick peek as to how LLVM handles non-multiple of 8-bit sizes. LLVM 2-bit integer. So I'm kind of curious how it handles this. The funny thing is, this has now turned into an LLVM stream. But to be fair, looking at my set of constraints and all the different weird bit sizes that they're using and stuff, I definitely don't want to do that by hand. I could, but I don't want to. This seems easier. Also, learning about LLVM is fun, you know. Long. Struct Bob. No, I want this to be an int. I want this to be an int. Where's my struct definition though? And what if we make this 4? Okay, so it takes the smallest int type that fits the entire thing. Oh, I didn't know that LLVM can have arbitrary sized integers. Oh, it can't. Width of bit field bar exceeds the width of its type. Value will be truncated to 32 bits. Damn. Interesting. Okay. Or is it with 2? Okay. Okay, so how do these int types work then, if that is something we could do? This int64 type. Int64 type in context. Ooh, okay, so you can define the... You can define arbitrary bits integers. Custom with int type. Gets the int type representing, it will be assigned the current context. Cool. That's neat. Okay. That is pretty cool. So we're gonna call this compile expr then, or compile AST, which is the same thing. And so to go back to all the way at the beginning, we're gonna comment all of this out, and we're gonna do cargo run so we can see our constraint being printed out again. Oh, actually we want cargo test, my bad. I love how there's a Rust package called parking lot. Okay. Just show output. Okay, that shows the graph here. So let's start with the easy ones, right? So if we want to, here's what we're gonna do. Here's what we're gonna do. AST.kind. First of all. So if we have a numeral, so any constant valued number, then might actually make these separate functions. AST kind, var functical, okay. So if our AST is a numeral, then we have to figure out what its type is. Because I think a numeral can actually be, yeah. So if it's a numeral, we're gonna match on AST.sortKind. And what we're gonna do is we're only gonna accept, actually. We're only gonna accept the bit vectors. So we're gonna say AST.sortKind. BV. Okay. So now we need the size of the bit vector. So that's just AST.kind.bv, AST.sort. So this gives us the type of the bit vector, which is bit vector of size 8. Let sort equals AST.sort. Let size equals BV sort.BV size dot unwrap, or if we're not getting a BV size back, we're going to return an error that says could not retrieve bit vector size, because that's not cool. If we have a bit vector, we should always be able to get a size. And then we're just going to return that straight out. Okay, so now we have the size of the bit vector. Gee, did we add that here? Yes, we did. What do you not like about that? Yeah, we'll get to the rest. The rest is to do. So now we have that. So now we make the LLVM type is self.context.custom with int type. Actually, let's match on the size just to get the nice types. So we get the correct types. If we have a validly sized bit vector, like a size 64, like a size 8, things like that, let's just return the correct type. 64 to self.context.i64 type. 128 self.context.i128 type. 32. And so if we have anything else, we return custom with int type. Custom. Okay, so that gives us a type. Hold on, my headphones just died. Let me change that. Okay, so now we want const int of arbitrary precision. We might just do const int from string because we're JITting once and then running a lot, so it shouldn't matter. So ast dot asbv dot well let me see. DV. T. Okay. So now what we should have is I think that should give us why are you still not recognizing this? Hmm. Values. What's a basic value? Okay, I guess we do have to do the ugly any value thing. Box. Okay, and this needs the LLVM context, lifetime. Cool. So I forgot one. I think I forgot one. I did forget one. Cool. Why do you not recognize the type of this thing? Is it this that you don't like? Okay, so here we have to do okay. That's fine. How about now? You recognize it now. Okay, for now, let's say we're gonna have to say we're gonna restrict ourselves to bit vector of size up to 128 because I haven't checked yet how to extract larger values from Z3. Z3 get numeral string. Numeral string. Let me look at an example for that. Z3 get numeral string. Okay, it looks like we just need to add an option to our Z3 wrapper. And again, this is why I cloned my own version of the Z3 Rust bindings, because like they're not complete when it comes to anything other than adding constraint and solving for them. C3 get numeral strings. Let me look at the exact API itself. Why binary string? Do they mean byte string? Z3 get numeral string. What's wrong with this? I just want to know what representation this string is. For numbers that don't fit into those basic types, we can use the get numeral string. Two APIs mix nicely. Well, thank you. That doesn't tell me what format the string is in. Okay, I think it's literally just decimal. Okay, that works. So, as U64. Wait, they define this on every AST? That's so dumb. Pub function as numeral string. No, they can't have possibly done that. Oh, just for BBs. Okay. And for now, let's just return the string. String new. Where did I do that in context? I think I added it before. Yeah, here. As I64, as U64, as numeral string. Okay, so here's what I'm going to do. We're going to say stir p is guarded call z3 to z3 get numeral string. And that takes the context and the AST. Okay, so that's self.context.z3 context and self.z3 AST. And I will actually wrap this myself because I don't want the string to go. Okay. And we need U. Z3 get numeral string. Context. And the Z3 AST. Now we have an int 8 pointer. So now we make our own string. So first, can this fail? Good question. Good question. Can this fail? It requires, I mean, we can check for null anyways, right? Like, assert stir p dot is null. So if that ever returns a null pointer, just crash. Fine. We can even could not get numeral string for That way we can even see what the AST was that we couldn't get it for. Self. Ooh, actually, hold on. I also added this. So that we get the last error that occurred. Okay, and then we convert this back from the representation into an actual string and return S. Cool. Sweet. So now .i28.const Okay, I guess for this one we still have to do the arbitrary precision thing. So here, let v vv dot as fuck it. Let's just keep that one as a default as well, because I don't really want to deal with it. That's not gonna, hopefully not gonna happen anyways. Otherwise, we'll deal with it. Const int. Now that's a good question. Do we want to sign extend or zero extend? Sign extension, LLVM const int. Let me look up the actual description of this because that's not going to be helpful otherwise. All right, obtain a constant value for an integer. Wow, thanks. Whether to sign extend the produced value. Whether to sign extend the produced value. Int of string and size. Okay. I've yet to is there a better description of in what cases it would sign extend versus when not? I guess that would only trigger for things greater than in 64? Mm-hmm. Pulse Kabul. Wait, but what was this constant FP thing then? Okay, well, we're just going to say don't sign extend. I don't know. For now, let's just deal with this. The way I see it, here's the way I see it. Given that we're passing 64-bit integers and all of our types are less than 64, I don't think it should matter. I don't think it should ever sign extend anything. So we're just going to treat it that way and move on. It should only truncate it, if anything. And we can see if the code is incorrect later, but dot const int bv dot as u64 dot unwrap. Here's what we do. 64 or 32 or 16 or 8. Val equals bv dot as u64. We're going to expect this to always return a value because it's a numeral. Like, if we're not going to get a numeral out of z3 for a numeral value, I don't even know. So, and then we're going to do the shitty thing where we match again. And now we're going to have 64. $32. 16. And 8. And then on that, we're going to call const int with val, and we're not going to sign extend. And that will be the return value of that. And then close this guy. If we have a custom bit width, we're going to say, we're going to get the string representation, bv.as numeral string. If stirp yeah, actually, because this could fail if we're calling it on the wrong object. Then here, we're going to return some of that. Then we're going to make this an option for a string. Okay. Okay, we don't need unsafe in here again. We're already far past unsafe at this point. Classic. Classic. Okay, what do you not like about this? Cargo check. What do you not like? What? Okay. String from S. What's wrong with this? Oh my god. It implemented it used it imported AST string. Oh, that's so dumb. Where is this defined? alloc string. Fine. Fine, we'll manually hardcode what kind of fucking string we want. As numeral string. Alloc string. There you go. You happy now? Alloc string. No? Standard. Hold on. Rust string. Yeah, it's just standard string. Oh, you have to like that, come on. Okay, we'll specify it here too. Now you have to be happy. Almost. We're getting there. Oh, geez. Okay. So method named found. Oh, is this get sort? I think. Is what it's called. Yeah, there you go. What? So why are you... So here... What does the tutorial return for this? That's actually important. Because when they compile something, oh, but they get to return a float value always. I don't get to do that. So yeah, we're gonna have to do box of din any value again. Okay. As numeral string, we expect this to work because, I mean, if we have a number, we should always be able to. Actually, can't I just... value for this guy. Okay, so now we can see if... Now we'll know. Yeah, so that should always work. And then all we have to do is we make a custom width bit type. Custom width int type. With the size being the custom bit width. And then we make a const int from string. Okay. So this way we're returning this value. Here we're returning this value. And then this is our LLVM value. And then out here, all we have to do is return okay with our LLVM value, our JIT values. I think it should not complain about this. At least not this specific thing. Okay. No, just not complain about that anymore. Okay. It's a little happier. Slowly but surely, we're making happy trees. U32. Okay, if my bit size doesn't fit into 32 bits, I'm gonna fucking cry. I don't think C3 handles that anyways, so we'll just do that. And then this takes the radix as well. Okay, so that's base 10. Come on, be happy. Match arms have incompatible types. Expected a reference. Okay, so we just borrow. Expected string radix found integer. What? What's string radix? Sure. Where are you defined? Decimal. Okay. Or so what do you not like now? Match arms have incompatible types. This is found to be of type inkwell values int value. Const int from string. Okay, fuck it. I'd wrap. Okay. So now is a bool value an int value? Now I'm actually kind of curious. Int value. Actually, so if we represented every Boolean as an integer that's just 0 or 1, the way C does, we could make our life a lot easier. Why don't we do that? Then we don't have to do this nonsense. Yeah, fuck it. Everything is an int. Int value. Can we do that? Let me think about this. Why would we not be able to do that? I can't think of a reason why we shouldn't be able to do that. So, fuck it. We'll change it if we have to. But as of now, I think that should work. Okay, so this is going to be of type LLVM context. Oh god. JIT values is going to have both lifetimes, C3 context and LLVM context. Is going to have the same. Not found in inkwell. Oh, I forgot. Classic. Classic. All right. Now we'll leave that at that. There's an int type in this case. Okay, so here we have to do this as well. Slowly but surely, we're whittling down the compiler errors. Ah, oh, so close. Oh, really? You can't recognize this? Oh, that sucks. Okay, so this is indeed hopefully unreachable, unless I'm super dumb. Unless I'm super dumb, this should be unreachable. Nice. Okay, so I mean, we can try just like compile a simple constraint that's just a number. Yeah, why not? Let's try it. Let's give it a try. Let me steal, because I always forget how this works. Let me steal this stuff. Let's write it a little test routine. So, inkwell context. Okay, so this is not what I want. Dot get global. Sure, why not? Get global. What do you want? You want a function? What do you want a function? Okay, fine, create. Okay, so now we have a context. What else do we need? We need a module. All right, let module context dot create module. JIT constraint, we call it. What else do we need? We need a builder. Create builder. And last but not least, an execution engine. How do I make one of those? Execution engine. Module.create JIT execution engine. Okay. Module.create JIT execution engine. We want some good optimization, I think, right? Yeah, fuck it, all the optimization. Optimization level. Now import it. What do we have? Fuck yeah, aggressive. All right, so now we have everything to make our code gen. We have the context, we have the module, we have the builder, and we have the engine. We just have to name them slightly differently. Context, module, builder, execution engine. Context, execution engine. Sweet. Now I just need to import this. Why do you not like this? Sure. Up. Okay. So now we can say codegen dots constraint. We'll also pass a function name, which is just going to be a string. The name is going to pass here, function name. Hey, I think we might be close to having our first JIT program running, hopefully. Dot JIT compile constraint. Constraint 1. Let me steal you guys as per usual. All right, by the way, I think I will have to go in half an hour because it just turned 3 and I have to call my parents before it's too late in Germany. But I will be back doing the exact same thing tomorrow, same time. We're gonna just continue doing this, and until we have a JIT constraint. No method found. Oh, we're gonna need the AST as well. We're probably gonna need dynamic anyway, so I'm just gonna add it now. Yes. Unwrap. Unsafe result dot call input buff is 0u8 2. Okay. Okay, print line. JIT function returned. Let's see what all of this gives me. Result. JIT. How do I get a pointer out of this? Just do as pointer, I think. Yeah, that seems to check out. All right. So far, so good. This is not quite gonna work yet. So what we're actually gonna do is the actual constraint is gonna be 1 equals 1, because that way we only have to do the binary expression one next to actually correctly lift things. So now if we do this, it should fail, and it should tell us that we have an unimplemented function that doesn't compile, hopefully. Found pointer value, but expected the int value variant. Ooh, it's not what I was expecting. Classic. Rust backtrace equals 1. Let's see where we're crashing. JIT compile constraint. Right into. Oh, of course. Duh, I'm dumb. So into pointer value, and this should be an int value. And so we're not going to do that one, but what we're instead going to do is we're going to say self dot compile ast constraint.into. And we're going to pass an empty hash map. Default result values equals that guy. And then that can also instead return an error though. So we're going to expect this to succeed. Expect could not compile. Actually, if we unwrap, we get what the actual error was. The result is an int value. Okay, yes. And then here, all we're going to do is return the result. Okay, that's not too bad. Function name. Should still fail, but now it should fail differently. Pilot AST, we're failing with not yet implemented. Okay, good. That's what we want to see. That is what we want to see. Can I? Yes. To do. Not yet implemented. Format. AST. For that one, okay? So now we know we haven't implemented this guy. Like really? Do I have to though? Text token. Yeah, whatever. Ooh, okay. So, failing in the same place. Panicked at not yet implemented. Print line ast.print verbose. Oh, whoops. Okay. Now it should print the last thing right before it crashes. And I'm guessing what we're missing is a function application. Yes. AST kind app. So here, okay, so for a function application, so first things first, we're gonna need to pass the input buffer type and the input buffer object and the size object so we can actually access them in our compiled code. So input buffer is going to be pointer value. And then buffer size is going to be int value. Okay, so we need to specify the context here. Again, context. All right, we're getting close. Gee, 1 second. Okay, so past all of that, what do you not like? Right. Right. So that, then this is buffer. Well, this is buffer size. Okay, buffer val, buffer size. Nice, okay, we're getting somewhere. Oh, this is just buffer. Okay. So let me comment this out for just a sec. App. So function applications, we're going to have two options. One, we are either going to have the result be a bit vector, or we're going to have the result be a Boolean, because, I mean, that's the types we support. So we're going to match AST dot decal. So let's get the declaration of the function that we're calling. So now we have our function declaration. What do we need from that? What we need from that is, first of all, we need to match ast.getSort. it might honestly be worth splitting on that first. So why don't we do that? Match ast.sort. C3 sort find bool. And then actually we're just going to have a function compile bool that literally takes all the same crap. And returns all the same stuff. I just want them to be separate. Because, so the main reason I'm doing this is because there are certain operations we can only do and only have to look for on bit vectors, and there are some that we only have to look for on Boolean values. So for example, like we don't have to ever be able to add Boolean values. That's not something that Z3 even allows you to do. So we don't have to look for it. What we're going to do here is, first of all, do this at the end. You stop complaining. Compile BV. Here, we're going to stick all of you. We can even actually, yes. So here's what we're going to instead do. We're actually just going to do compile BV numeral. Because then we actually eliminate some significant rightward pressure from our code we don't have to deal with. Numeral, here we do self dot compile numeral, compile BV numeral with our AST, our JIT values, our input buffer. Might honestly be smart to have a structure that's just like a constrained compilation context, instead of just passing 4 arguments each time. It doesn't make much sense. But for now, we're going to keep it. Get rid of all of this. And then here we're going to do the exact same thing. And we're just going to say compile BV app. And then here, copy and paste this one more time. Yeah, I think I'm definitely going to make a constrained compilation context or something that just holds these all for me, so that there's some like logic to these, because as it is, this is kind of messy. It doesn't need to be. None of this ever changes, right? We're during a compilation context, the only thing ever changing, the JIT values gets updated, the input buffer stays the same, the buffer size stays the same. The only thing that changes is which AST we're compiling. And so, yeah. Yeah, so we're gonna do that, but for now, sort kind bool. And here we have sort kind BV. And so for now, compile bool app, because we only, right now, we don't have to deal with Boolean variables yet, and we're not going to. All our variables are going to be 8-bit integers, if you remember, 8-bit bit vectors. So all we're going to do is just here, we're still going to do this, but the only thing we really have to care about here is, I think, applications. Let's get return self.compile bool app. And again, we're going to stick all this nonsense in here. So this is like a very shitty version of the visitor pattern, if you will. But I'm sure it's gonna be fine. Okay. Put this guy back. And then this is get sort. Okay, unwrap this guy. PV. And then these that can actually deal with their correct types already, so we have their helper functions. Here we're gonna do cool. All right. So, yes, you're gonna take a bool. You're gonna take a BV. You're gonna take a BV. That thing is happy. And then what do you mean no? Okay. So we can move that out here. Then we also, okay. Just gonna panic so to make this guy happy. Rename that BV. Rename that BV. And Yeah. So the BV numeral doesn't care about these guys. Let's leave it here for consistency. Almost. No? Not quite. Okay, here we're also going to do, we're just going to leave these all as to do for now. Because that way, once we run into them, we'll get the error and then we can fix it as it happens. What are you? Why are you not happy? Oh, that's why. All right. Once this compiles, I'm going to call it for today. Yes, okay. So I'm going to call it for today. Because, and we'll be, like I said, I'll be back tomorrow at the exact same time. And we'll pick up where we left off. We made some good progress. We'll add the applications as they come in for the different operations. And I think the bit vector ones are going to be the main ones because there's a lot of them. For bool, I don't think we have to do much. But so far, this LLVM wrapper library, actually pretty nice. Actually pretty nice. Alrighty. Thank you guys for hanging out. Thank you guys for watching. And I will hopefully see you guys tomorrow. Bye.